Yes, hi, this is George Larakis again, and today I would like to discuss about how we can find trigonometric integrals. And actually, by how to find trigonometric integrals, I mean integrals that they are not one of these, integrals that we already know how to find, like the cos of an angle, the sine of an angle, which you can directly apply the rule. So here, actually, I would like to discuss about finding integrals, like more complicated integrals, and what we can do in order to find them. And actually, here we have some cases. So let's say the first case, it will be the integral of sine x cos x dx, let's say here to the power of k, and this is to the power of L. So that's the one category of the integrals that I will show you how to find. And now in this category here, we have of course some subcategories. So let's say I. So if k is odd, so let's say you can write it as 2n plus 1. What you do is you save a power of sine, and then you substitute the rest from the formula sine square x plus cos square x is equal with 1. We substitute the rest, which will be a multiple of 2 from this formula here. So we'll substitute it, the sine square x equal with 1 minus cos square x. And also we substitute u is equal with cos of x. So what it will happen? Let's see what it will happen. As I said, if we substitute, let's say instead of k we have 2n plus 1. So that means that how we write this, we said we keep 1 sine x. So that means that you write sine x, and then you will have only sine in the 2n. So in that you can write it as sine square x to the n. So and then you substitute whatever sine square x equal with 1 minus cos square x. So that will be here 1 minus cos square x to the n. And then of course we have the cos x to the L dx. And now what we have also, we said that we substitute also that u is equal with cos of x. So that means that du over dx is equal with minus sine x. So, and from that, if you solve for dx, you have that dx, it will be equal with du, actually minus du over sine x. So, and if you continue here now, what we have that this will be equal with sine x. Now this here, it will be it will be some power of like it will, if you expand this 1 minus cos square x to the n. That will be a polynomial of, which will be a function of cos x. And of course here you will have the cos to the Lx, and then we said we substitute whatever dx equal with du over sine x, so with the minus in front, so that should be dx over, du over sine x. So and now you see that this cancels with this, and and then what do you have? This here we said it will be, let's put it as a function of cos of x. When you develop this 1 minus cos square x to the n, when you expand it, you will get some function of cos x. So, and now, since we have that u is equal with cos x, so, and we don't have any more sine x, so what you will have inside, it will be a function again of, let's say, capital F of cos x, with du. The minus can be incorporated here. So, and because we said that cos x is equal with u, so that means that you have f of x, f of u du, and that of course, in order to find this is very simple. The only formula you need to know that you have to use the formula from integration, that the integral of x to the n with respect to dx is equal with x to the n plus 1 over n plus 1, and of course instead of x we use u. So that's the theory behind this case here. So, and again, the case is we have an integral of the form sine x to some power times cos x to some other power, and we're in the case that the power of the sine is odd. Because I like to generalize things. This is also a case where L or the power of x can be 0. So what do I mean by that? I mean that you can have it only the one of these two. Like you can either have sine x to some power, or you can have cos of x to some power. The power of one of these two is equal with 0. Of course, both of them, they cannot be 0 at the same time, because then you will just have one. So it's it's not the case that we are studying. So let me do an example, because I know that this will help. Let's say find the integral of sine to the third x times cos square x dx. So the power of sine x is 3, which is odd. So that means that we can use what we just said in the theory. So that means that we said we save a power of sine x, sorry. And then, you write the rest. So it will be sine x times sine square x. Then of course times cos square x dx. And always here we substitute that u is equal with cos x. So that means that du over dx is equal with minus sine x. And from this you have that dx is equal with minus du over sine x. So if we go and we substitute now we're going to substitute the dx, what we will have the integral of sine x, and also we said that we substitute the sine square x equal with 1 minus cos square x, and of course we write the cos square x that we have here, and of course we substitute the dx from here, so that should be equal with minus du over sine x. So now this with this cancels, and what do we have? We have now that we can go directly and substitute whatever cos x equal with u, so that means that we will have 1 minus u square times u square times minus 1, so we can put the minus here, and of course this is with respect to du. And now if we do the operations here, we will have minus 1 times u, it's minus u square, and minus the minus plus u square times u square, it's plus u to the 4th, and of course this is with respect to du, and let's finish it here. So, like the integral of this here, it's minus u to the 3rd over 3, and the integral of this here, it's u to the 4th over 4, excuse me, u to the 5 over 5, sorry. And finally, because the initial integral was in terms of was in terms of x, so that means that we can say that this is equal with, go back and we substitute the initial variable, which was x, so we can say that this is equal with minus cos x to the 3rd over 3 plus cos to the x, cos x to the 5th over 5 plus, of course, sin. So, and that's about it. So, now, let's continue. The second, let's say, subcase of this, it will be when the power of cos to the L is odd. So, we do exactly the same, with the only difference that here, of course, when you spread this here, so we said this L here is odd, so that means that you keep a power of cos, and then the rest it will be cos to some even power. So, and then of course again you use the fact that cos square x is equal with 1 minus sine square x. So that means that you go here and you put the cos square x that you will have inside, you will put equal with 1 minus sine square x in some power n. And of course here you have the sine x to the k. And and here you substitute also that u is equal with sine x, and from that you have that du over dx is equal with cos x. So that means that if you solve for a dx, you will have that dx is equal with du over cos x. So if you go and you substitute this dx equal with this, you will have du over cos x. So, and you see now that this cancels with this, and then if you substitute again whatever sine x equal with u, what you will have a function of u, polynomial function of u, which you have to find the integral with respect to u also. So I mean, it's exactly the same case as before. So I don't think so that it's necessary to do an example here. And now the case which is different. I mean, we are still on this kind of trigonometric integrals. So now, when we said k is odd, L is odd. So I mean, if you have that the one is odd and the other is even, you work on the one that is odd. So, but what about if both of them they are even? So that's the third case where k and L they are even. So in this case, what we do is we use what we call the double angle or the half angle. So what do I mean by that? I mean, you substitute whatever sine square x is equal with 1/2 times 1 minus cos 2x, and you substitute whatever cos square x equal with 1/2 times 1 plus cos 2x. So I mean, this is these two are some formulas that you can derive it from trigonometry, but here you just have to use it as they are. You don't have to prove anything. So now let's see how we can work this out. So yeah. So since these k and L they are even, so that means that you can write this k as 2n, and you can write this L as 2m. So which means that you can write this thing as sine square to the n and x, of course, and cos x square to the m dx. And now, of course, you can go and substitute the sine square x that we have here equal with 1/2 times 1 minus cos 2x to the n times the cos square x. You substitute it from here, and it will be times 1/2 times 1 plus cos 2x, and of course all this integral with respect to dx. Okay, and of course you have to put this to the n and this to the n, which is not a problem because this would be just a constant. So And now what we have here, we have of course the number 1/2 to the n and here to the m, sorry. Of course here to the m. So you have these numbers 1/2 to the n plus m, which will be a number, so you can take it outside of the integral. And then what it will be left, it will be the 1 minus cos 2x to the n times the 1 plus cos 2x to the m. So this, it will be a polynomial of cos 2x. So when you do this, this multiplication, like this polynomial times this polynomial, you will have a polynomial, let's say f of cos 2x dx. So, you know, I mean, the numbers we said, we just ignore them because, you know, it's you just take it outside of the integral. So now here, to find this integral here, you know, you just have to, it's pretty easy because you just have to substitute u is equal with 2x, and you know, and then from that you have that du over dx is equal with 2, and you know, it's pretty simple integral. I will do an example right after this, after I finish with this, and you will see that it's pretty easy. The only thing is that sometimes you might have, because here you have powers of n and m, you might have this to some power, like you might have it to some even power, okay? You know, because when you multiply, you know, like this, you might have, let's say, cos square 2x square. So in this case, what you do is you start again from the beginning. What do I mean by that? You have to rewrite the cos, let's say, square, the cos 2x square, you write it as using this formula. So that means that it will be 1/2 times 1 plus cos the double angle, now it will be 4x. So, and you work this way down until you don't have any more even powers. So let me do an example to see how this works. Okay, to find the integral of sine x to the 4th times cos x square dx. So as you see here, both the powers of sine and cos, they're even. So that means that we have to use what we just said. So okay, so we said we have to write, we have to substitute whatever sine square x equal with 1/2 times the one minus cos 2x, and cos square x is equal with 1/2 times 1 plus cos 2x. So that means that let's continue here. So we have that you know, the sine to the 4th x, it's sine square x and all square. So that means that we can write, you can write it as 1/2 times 1 minus cos 2x square. So that means that you put a square here, and of course you put a square here, and then the cos square x, which is here, we just substitute it from here. So that should be times 1/2 1 plus cos 2x, and of course with respect to dx. So now when you have 1/2 to the power of 2 and 1 also to the power of 3, so that's 1/8. So you take this 1/8 outside of the integral, and now what you have inside the integral, if you expand this here, it will be 1 minus 2 cos 2x plus cos square 2x, and then of course you have to multiply times this here, so that should be 1 minus cos 2x, so dx of course. So now let's do the operations to see what we have. So we have well, this is plus here. So it's from here. So what do we have? We have 1/8, and then we have, if you do the multiplication, 1 times 1 is 1. 1 times cos 2x is plus cos 2x. Now this times 1, it's minus 2 cos 2x, and then this times this is minus 2 cos square 2x, and finally this times this will give you plus cos square 2x, and this times this will give you plus cos to the third 2x dx. Okay, so now if we rewrite this, what we have okay, so we have 1/8, and inside we have 1. Now plus cos 2x minus 2 cos 2x, that should be equal with minus cos 2x. So let's erase, so we know that we calculate this, and now you have minus 2 cos square 2x plus cos square 2x, so that's minus cos square 2x, so this cancels with this, and finally you have the plus cos to the third 2x, and of course all this is the integral with respect to x. So let's erase a little bit. So now this is equal with 1/8, and of course now